If you tried to manually draw out the structural blueprint for the microchip inside the device you are listening to this on right now, it would take you and your descendants centuries to finish the job.
It really is a staggering visualization. We've basically reached a point where the physical scale of what we're building entirely defeats human capability.
Yeah, just generations of engineers, right? Handing down these massive hand-drawn blueprints for a single processor.
Exactly.
And, well, that is exactly what we are unpacking in today's deep dive. We are exploring the art and science of VLSI, very large-scale integration.
Specifically, physical design automation.
Right. We're going to look at the incredibly complex process of taking a logical blueprint, the netlist, and turning it into this physical, microscopic city of billions of transistors.
And we'll see how the software that does this, electronic design automation, or EDA, basically operates at the intersection of computer science, electrical engineering, and...
Yeah, what honestly feels like dark magic.
Yeah, the magic aspect is something you actually hear a lot in this field.
I mean, I kept seeing that word in the source materials.
Well, mostly because EDA solves the ultimate chicken and egg problem of silicon scaling. Every year, the industry demands these smaller, faster, more power efficient chips.
Right.
But to design a chip with tens of billions of transistors, you need incredibly powerful computers running incredibly complex software.
So wait, to get the powerful computers, you first need more complex chips to build them with.
Exactly. It's a paradox. And EDA is the bridge that breaks that loop. It automates the design of the next generation of hardware using the current generation.
Wow. Okay, so to really understand how that bridge works, we have to look at the fundamental split in the design process itself. It's basically a divide between pure logic and physical geometry.
Right. On one side, you have logic synthesis.
Yeah, the abstract math.
Yeah.
Writing out the Boolean logic, the true and false gates, mapping out exactly what the chip is mathematically supposed to do.
And this side of the fence gets a lot of the glory. It's highly appreciated work.
It's the sexy part of chip design.
It is. But the irony is that the human brain is actually terrible at raw logic at that scale. Keeping track of, say, 100 intercepting true and false statements in your head.
Oh, it's virtually impossible. I lose the thread after 3.
We all do. Human cognition just isn't optimized for massive parallel Boolean logic.
But then you have the other side of the fence, which is physical design. Taking that abstract logic and translating it into actual shapes, coordinates, and physical wires on a silicon wafer.
And this part is often unfairly viewed as just like the heavy lifting, the grunt work.
Right, but from an evolutionary standpoint, humans are actually amazing at vision. We're naturally wired to process spatial relationships and geometry almost instantly.
We really are. I mean, if I put a complex maze on a piece of paper in front of you, your eyes can sweep over it and spot the dead ends in seconds.
Yeah, you just intuitively understand the space, which, begs the question, if human vision and spatial reasoning are so naturally suited for this, why do we need massive automation? If we understand geometry so well, why aren't humans just laying out these blocks visually?
Because of the primary antagonist in every modern engineering story. Scale. Human vision is brilliant conceptually, but it completely breaks down physically when the maze you're trying to solve is functionally the size of Texas.
Oh, wow.
Yeah, a maze the size of Texas consisting of 1 billion intersecting paths stacked in 3 dimensions. The automation isn't there because computers are better at spatial reasoning than we are.
Dang arts.
No, they really aren't. The automation is required to take a highly visual problem and translate it into a computationally solvable one so a machine can brute force the scale.
Okay, and to teach a computer how to see that puzzle without instantly running out of memory and crashing, we've had to impose some incredibly strict rules.
Yes. The documentation frames this as a strictly forced evolution.
Forced evolution. I love that. We are forcing the software architecture to adapt to the physical limitations of the hardware, and these rules are uncompromising.
Very uncompromising.
Like the absolute ban on using floating point numbers for coordinates. The mantra in the sources is, floats lie, integers don't.
Right, because you're dealing with massive grids scaling up to 1 million by 1 million units. You have to use large integers like N64 for every single coordinate.
Wait, here's where I have to push back a little. Why are floating point numbers so bad? Aren't floats technically mathematically more precise?
Because they give you decimals.
In the context of computer science, floating point math is essentially an approximation.
Okay.
I mean, when a computer has to calculate a complex fraction, it eventually runs out of memory to store that exact number, right? So it just rounds off the end.
Right, but if you're Calculating physics in a video game, rounding off a thousandth of a decimal, doesn't really matter.
Exactly. But here, the stakes are physical. When you multiply a microscopic rounding error across a billion physical objects on a grid, you inevitably get drift.
Oh, I see.
Close enough computation means two microscopic copper wires that were supposed to be parallel end up overlapping by a fraction of a nanometer. And in a physical chip, an overlap is a short circuit. The whole device is dead.
The entire device is dead. So as the mantra goes, floats lie. Integers force absolute precision. A logic gate is placed at coordinate 50 or 51.
There is no 50.0001.
Exactly. It locks the entire design to a rigid, absolute grid.
Which naturally leads to the next massive constraint, which is Manhattan geometry. You're defaulting entirely to rectilinear shapes.
Yes, the entire chip is constructed using 90-degree vertical and horizontal lines.
That is so wild to me. Very rarely you might see like an abstract 45-degree line, but arbitrary curves are completely forbidden.
Completely.
It's like playing a game of SimCity, but you are absolutely banned from building anything other than perfectly straight right-angled roads. It just feels like you'd be wasting space by not taking a direct diagonal path.
It definitely seems inefficient visually, but computationally it is the only way the system survives. There are three main reasons for Manhattan geometry.
Okay, what's the first one?
Design rule checking, or DRC. The software constantly has to verify that millions of shapes aren't placed too close together. Calculating the exact distance between two straight-edge rectangles is computationally cheap. It's just basic subtraction.
But calculating the distance between two organic curved polygons.
That requires complex calculus.
And running calculus billions of times per second is how you melt your servers.
Precisely. The second reason is that it makes the routing algorithms much faster, for the exact same mathematical reasons. And third, it allows for predictable parasitics.
Wait, parasitics? Like electromagnetic interference?
Right. When microscopic wires are packed tightly together, their electromagnetic fields interact. If you use pure 90-degree angles, the interference models are mathematically predictable.
So the engineers can calculate exactly how much crosstalk will happen and compensate for it.
Exactly. If you allow arbitrary angles and curves, the fields interact chaotically. The interference becomes impossible to model accurately at scale.
That need for absolute predictability makes sense when you look at the raw numbers. I mean, we are dealing with 10 to the 9th power. 1 billion physical objects on a single chip.
That's staggering.
There are barely any exceptions to this scale either. You might cap polygon vertices at 10 or limit your keep-out zones, the do not build here blocks, to a handful, but everything else is in the billions.
And that staggering scale is what forces the software engineering itself to be so disciplined. You really can't write sloppy code when dealing with a billion objects.
Right, so let's talk about the C++ performance doctrine.
Yeah.
Because this is where the software engineers really have to eat their vegetables.
Oh, yes.
To manage a billion integer coordinates, you can't just write flexible, modern code. The golden rule is that algorithms must be brutally simple.
Because simple means fewer moving parts. It's easily verifiable and hard to break.
Right. They rely on C++ for absolute memory control. But they impose these incredibly strict rules on how it's used, avoiding virtual functions entirely, for example.
Yeah, to prevent vtable cache misses.
And preferring unique pointers over shared pointers to ensure there's a strict ownership hierarchy. No cyclic dependencies hiding memory leaks.
It makes total sense. At a scale of a billion objects, a single cache miss per object doesn't just slow the program down.
It crashes it, right?
It guarantees the software will crash before it ever finishes compiling the chip layout. A layout that should take 3 hours suddenly takes 6 months. The software architecture has to mirror the hardware, rigid, direct, and predictable.
But there is this beautiful irony in their modern workflow. So to build these unforgiving silicon structures using this highly restricted C++A, their actual first step is prototyping in Python.
Yes, which is practically the opposite of C++A.
Right. It's so forgiving. So our first step is to use forgiving Python and have an AI copilot help us translate it.
Well, the tools matched the phase. Python is the language of human brainstorming. It allows an engineer to quickly test the math of a new routing algorithm without fighting memory pointers for a week.
Oh, that makes sense.
Once the math is proven, then C++ is the unforgiving reality of the hardware execution.
It's that forced evolution loop in action again. Scale demands simple memory, which forces integer math, which requires Manhattan geometry, built on disciplined C++ plane.
Exactly.
So we have the rules engine, we have our rigid grid, but having the rules isn't the same as actually solving the puzzle. How does the software physically figure out where to place a billion wires without gridlocking itself?
This is where we transition into the advanced toolkit, the core algorithms.
Okay, so the first major step is multi-level hypergraph partitioning. The goal here is to take the entire logical netlist and divide it into balanced physical blocks while strictly minimizing cut nets.
Right, cut nets being the wires that have to cross between different blocks. They use clustering algorithms, specifically something called FM refinement, Fiducia-Mathesi's refinement.
Right, and minimizing cut nets is critical because every time a signal has to cross a major block boundary, it degrades performance, right?
Yes, it consumes more power, introduces delay, and eats up routing tracks.
So it's basically like trying to organize a massive group of friends into different cars for a road trip. You want roughly the same number of people in each car, but the primary rule is you don't want to split up best friends.
That's a great analogy.
The cut nets are like the text messages between the cars. If
Yeah.
everyone is constantly texting someone in a different car, it's just chaotic. So how does FM refinement actually solve that?
It's an iterative swapping mechanism. The algorithm starts with an initial, somewhat arbitrary division. Then it looks at a single logic gate and calculates, if I move this gate to the other block, does the total number of external wire connections go down?
And if yes, it swaps it.
Right. But the clever part of FM refinement is that it allows for temporary hill climbing. It will sometimes accept a swap that actually increases the cut nets temporarily.
Wait, really? Why would it do that?
If it unlocks a sequence of future swaps that ultimately lead to a much lower overall number, it constantly passes back and forth until it settles on an optimal layout.
Oh, wow. Okay, so once we have the logic partitioned into neighborhoods, we have to deal with the physical space. That brings us to rectilinear Voronoi diagrams.
Yes.
Now, a standard Voronoi diagram maps out territories based on the absolute shortest distance to a point, like a bird flying. The boundaries look like organic soap bubbles pressing against each other.
But since we're restricted to Manhattan geometry.
Right, the rectilinear Voronoi recalculates those territories using only 90-degree paths. So the bubbles become these jagged, blocky zones. What is the actual utility of doing that?
It maps the physical constraints of the neighborhood. By calculating the rectilinear distance to the nearest obstacles, like the boundaries of other components, the algorithm instantly knows exactly how much empty spatial capacity exists in any given corridor.
Ah, gotcha.
This is critical for wire sizing and buffer insertion. If a corridor is too narrow, you physically cannot route a thick power wire through it. The Voronoi diagram gives you a mathematical map of the available real estate.
Which sets the stage perfectly for global routing. This is where the software assigns wires to general regions. It's not locking in the exact microscopic track just yet. It's mapping out the general highway system.
Exactly.
And it has to navigate placement blockages, capacity limits for vias, which are those microscopic vertical tunnels connecting different layers, and the alternating layer direction rule.
Right, the 3D aspect.
Yeah.
Yeah.
Metal layer 1 only runs horizontally, metal layer 2 only runs vertically, metal 3 is horizontal again. Why do they enforce that alternating rule so strictly?
Because without it, the routing algorithms would constantly box themselves in. If you allow wires to run horizontally and vertically on the same layer, you inevitably create walls of copper that block other wires from crossing.
Oh, so you basically build a fence that traps your own signals.
Exactly. By enforcing alternating directional layers, you create a predictable 3D transit system. If a horizontal wire on layer 1 needs to travel north, it drops a via, jumps up to vertical layer 2, travels north, and then drops another via to jump back down.
It ensures there is always a path available. And
Yeah.
it's so elegant. But calculating the most efficient path for every single connection is where the math gets genuinely terrifying.
It really does.
They use a concept called Steiner forests. A Steiner tree problem asks, how do you connect multiple points using the absolute minimum total length of wire? You want to create a minimum cost forest. But here is the massive catch.
The NP hardwall.
Yeah. The math reveals that brute force enumeration of every possible Steiner tree at the scale of a microchip is an NP hard problem. It is computationally impossible.
Not within the lifespan of the universe, no.
So wait, we are building the most precise, advanced physical architecture on the planet, and at the core of the routing, we literally just give up on finding the perfect path. We just settle for near optimal.
Well, if we connect this to the bigger picture, that is the defining line between theoretical mathematics and engineering. Mathematics demands the absolute provable minimum path. Engineering demands a functional chip by Q3. So instead of explicit enumeration, the software relies on approximation algorithms, specifically union find and primal dual approaches.
How does union find bypass that impossible math?
Instead of trying to map the entire forest from a top-down perspective and calculating every possible global branch, Union Find operates locally. It looks at the individual pins that need connecting, searches the immediate grid, and snaps to the nearest available routing resource.
Oh, so it just grabs whatever is closest and builds the tree organically from the bottom up.
Exactly. It guarantees that everything gets connected efficiently without ever calculating the mathematically perfect global tree. It might use slightly more copper than the theoretical ideal, but it runs in minutes instead of millennia. It's a brilliant compromise.
That is incredible. Okay, so we've partitioned the logic, mapped the spatial capacity, and routed a billion wires using near optimal mathematical shortcuts across an alternating 3D grid. The physical layout is done.
Almost done. There is a final invisible dimension to this puzzle.
Time. It's not enough for the wires to just connect safely. The electrical signals traveling through them have to arrive at their destinations at exact microseconds.
The temporal dimension is arguably the most complex part of physical design. We're talking about the clock tree.
Right, specifically moving from traditional zero-skew designs to a prescribed skew DME clock tree. DME being deferred merge embedding.
Correct.
And the core of this is the useful skew flow. So let's break this down. The clock is basically the heartbeat of the chip. In a zero skew approach, the goal is to have every single logic gate receive that clock tick at the exact same 0-second mark.
Which is logically sound. You want all components synchronized perfectly to the same metronome.
But practically, it creates a nightmare.
Yeah.
Because some gates are further away from the clock source than others, achieving zero skew means forcing the software to do incredibly unnatural things.
Like deliberately zigzagging wires.
Exactly. Making a short path artificially longer, just so the signal arrives at the same time as a naturally long path. It wastes space and power. So, useful skew abandons that. It intentionally introduces clock delays to different parts of the chip.
Yes, intentional skew.
But my first instinct when reading this was, doesn't adding intentional delays actually slow the whole chip down? It's like telling people a meeting starts 5 minutes later.
It's deeply counterintuitive, I know. But manipulating the skew actually reclaims timing slack and prevents the chip from failing. Think about a setup violation.
Okay, what happens there?
A logic gate is waiting to capture a piece of data the exact moment the clock ticks. That tick is the capture edge. But let's say the data is coming from the other side of the chip, traveling down a congested path. The clock ticks, but the data hasn't arrived yet.
It gets there a fraction of a nanosecond too late.
Right. That's a setup violation. The data wasn't ready. In a rigid zero skew design, that chip is broken. Your only option would be to rip up the physical design and try to move the cells closer together.
Which destroys your beautifully routed spinor forests. You'd be unsolving the puzzle you just spent weeks compiling.
Exactly. But with useful skew, the software identifies that specific gate and intentionally delays the clock signal traveling to it. It slows the heartbeat for that one component.
Oh, wow.
Now, the delayed clock ticks a fraction of a nanosecond later, and the delayed data arrives perfectly on time. The capture edge and the data alignment are synchronized. You fixed a severe physical geometry problem purely by warping the temporal delivery of the clock.
That is genius. And it works in reverse too, right? For hold violations, where the data arrives but then disappears too quickly before the next clock tick can capture it.
Yes.
The software just adds padding to the data wire, physically slowing the data down so it holds in place long enough to be registered. DME calculates these optimal delay points and embeds them dynamically.
It really is the final layer of the architecture. You are balancing spatial geometry with temporal physics.
The engineers are literally using time manipulation to pave over the physical imperfections of the routed grid.
That's a great way to put it.
It is genuinely awe-inspiring when you zoom all the way out.
Yeah.
We start with raw, abstract Boolean math. But because the physical scale is so astronomical, the engineering undergoes this ruthless forced evolution.
We ban floating point numbers.
We force everything into right-angled Manhattan geometry. We write brutally stripped-down C++ to survive the memory constraints. We use Union Find shortcuts to cheat impossible routing math. And finally, we intentionally warp time itself just to make sure the signals arrive before the clock ticks.
It's honestly one of the most sophisticated achievements of human ingenuity. We've automated the construction of cities that are too small to see and too complex for the human mind to fully comprehend at scale.
So to you listening, the next time you pick up your smartphone or open your laptop, try to look past the smooth glass. Think about the millions of rectilinear polygons, the fiercely protected integer grids, the alternating 3D highways, and the intentionally delayed useful skews firing perfectly under the hood.
It is an absolute masterpiece of automation.
To wrap up, I want to leave you with a quote from the engineering documentation that perfectly captures the physical reality behind all this abstract math. Chips don't lie, but they do get hot.
They certainly do. And looking at the sheer weight of the constraints we've explored today, it leaves me with one final, very provocative thought.
Oh, what's that?
Well, if our entire physical design toolkit today, every algorithm, every Voronoi diagram, every routing forest, is strictly dictated by the mathematical limits of 2D Manhattan geometry and C++ memory constraints, what happens when we inevitably transition to advanced 3D quantum architectures or synthetic organic computing?
Oh, wow.
When right angles and rigid integer grids simply no longer apply to the physical substrate, will we have to discard this entire paradigm? Will we need to invent an entirely new mathematical universe just to build them?